It is a pleasure to present our ICLR Spotlight paper on geographic location encoding with spherical harmonics and sinusoidal representation networks with my collaborators Konstantin, Klemmer, Esther, Rolf, Zbinden and Devis, Tuia. Learning representations of geographical space is important for any machine learning model that integrates geolocated data. Let's take species identification as an example. Classifying images of animals with a common vision model yields about 60% top 1 accuracy on the iNaturalist 2018 benchmark dataset. Adding additional location information on the spatial distribution of species boosts this accuracy by an additional 10%. Traditionally, spatial interpolation approaches are used for these problems. However, they scale poorly with large datasets, and the choice of distance metric or kernel similarity introduces strong assumptions. Instead, recent works have introduced location encoders that are learnable functions that project longitude and latitude coordinates into a vector representation. These networks learn an implicit neural geo-representation of the training data. They scale well to many test data points as they just perform inference with a small neural network in linear time. As neural network, the FCNet introduced by Oda et al. Is used broadly. It is a multi-layer perceptron with a ReLU activation function and skip connections. However, inputting longitude and latitude coordinates directly into the FCNet is not optimal. Hence, recent research has focused on finding effective location embedding functions that project coordinates into higher dimensional vectors with sine and cosine basis functions, which is similar to Fourier series. In this work, we propose a novel location encoder that first uses spherical harmonic basis functions and then sinusoidal representation networks. Sirens are multi-layer perceptrons with sine activation functions and are broadly used in learning implicit neural representations. Let's focus first on spherical harmonics. Spherical harmonics are orthogonal basis functions defined on the sphere. They are implemented with associated Legendre polynomials of different degrees L and orders M that provide increasing frequencies. Each harmonic basis function can be weighted by a coefficient. With an unlimited number of weighted harmonics, we can theoretically approximate any function on the sphere. In terms of location encodings, we can interpret these weighted spherical harmonics as a simple location encoder with spherical harmonic location embedding function, followed by a one-layer linear neural network that provides the weights. Following this analogy, we can replace the linear network with a more complex neural network like a multi-layer Siren, which helps the location encoder to approximate more complex functions at higher resolutions with fewer spherical harmonics. Spherical harmonics are well defined on the entire sphere, while sine-cosine basis functions in existing location embeddings like in Grid and Sphere C+, assume a rectangular domain of longitude and latitude. On a sphere, this assumption is violated at the poles, as we see when plotting the checkerboard classification accuracy at different latitudes from north to south. Here, Grid and Sphere C+ decrease in accuracy at high latitudes due to artifacts in the predictions near the poles. Location encoders based on spherical harmonics remain accurate even at high latitudes, as they better represent the spherical geometry of our planet. Quantitatively, we evaluate the cross product of positional embeddings and neural networks on 4 representative datasets in the paper. First, we see that the naive approach of directly passing coordinates into the FCNet is not performing well. This highlights that ReLU networks like FCNet need location embedding functions for good performances. Second, we see that spherical harmonic basis functions work well with all neural networks, including a simple linear layer. Similarly, Siren performs consistently well across all location embedding functions, including direct embedding, where the previously used FCNet did not perform well. Overall, this highlights that Siren with sine activation functions does not need positional embedding functions for good performances. In fact, we show in the paper that a single Siren layer is equivalent to a grid embedding function if some weights and biases are set to specific values. In conclusion, our paper provided insights into best practices for location encoding for large-scale geographic data. Concretely, we can recommend Siren as a neural network for any location encoding problem and spherical harmonic basis functions for global scale problems where the spherical geometry of our planet matters. You can find further details and results in our paper. The source code is available on GitHub. Please reach out with further questions to my email. It was a pleasure to present our work, and thank you very much for listening.